right, let's go and review some things that we've talked about the last several lessons now. We've got pictures and proportions we've been working on. We're going to add another picture today to this. But one of the more recent pictures specifically, we took a triangle and said that if I were to bisect one of the angles of the triangle, it would divide the opposite side, not necessarily bisect it into equal parts, but it would divide it so that the ratio of these two segments is to each other as the ratio of the other two sides. In other words, class, we could say that, say it with me, segment is to segment, a side is to side. And again, if you're going to go with this segment here first and this segment second, then the side that touches this segment would be the first side. And every time I've shown it, I've always shown it the other way around, right? Standing straight up, but you could do it with any angle bisector. But anytime there is an angle bisector, class, we remember that segment is side. Good. We said the same could be true if we were to bisect an exterior angle. This is going to look awful, but if I were to extend this and bisect this angle, well, be a little bit challenging, because this particular angle would actually be going upward, so you'd have to go through this way downward here. Maybe I will not confuse you too bad. I was trying to get creative, but maybe we'll get less creative here. And we'll actually take an angle bisector that easily hits the other side and bisect an exterior angle. Well, it's going to divide this external side as well, or this opposite side as well, but it's going to divide it rather externally. So that, class, segment is to segment, as side is to side. And if we called this L, M, N, O, P, for instance, in letters, what would that proportion look like? Jamie?
Would be segment PL is to PN as NL is to MO.
Well, you said that this segment here, good, is to this segment here, good, as this side here is to what other side?
Would be MN.
MN would be your other side. There we go. All right, so making sure we're good to go with those proportions. We then transitioned, though, into talking about polygons, which are similar. What does it mean for polygons to be similar, Ethan?
To have equal angles and sides that are proportional.
Well, those are requirements to be similar, right? Equal corresponding angles, proportional corresponding sides. But just in general, what does similar mean, Chris?
They're the same.
If I was trying to explain it to Chloe, how would I explain to Chloe that these are similar?
Well, they look the same.
But they're not the
same size.
Same size. So they have the same shape, but not the same size, would be how we explain it. But the requirements was what I was going to ask next. Proportional sides, equal angles. And we said for two polygons to be similar, they also have to have the same number of sides, right? We said that a quadrilateral will never be similar to a nonagon. Couldn't be. They have different numbers of sides. You couldn't get, and different numbers of angles. But we said that if you had two regular nonagons, would they be similar, class?
Yes.
Yeah, they'd have to be, wouldn't they? So two squares, would they be similar? Always, sometimes, never?
Always.
Always. They'd have to be similar. They could also be congruent. By the way, we said if you had congruent figures, they are also similar, right? They just happen to have the same size. What's that ratio of any two corresponding sides, Kendall? We said proportional sides, meaning they all have equal ratios. We call it the ratio of? Similitude. What would be the ratio of similitude for congruent figures, Audrey? Anyone?
1 to 1.
1 to 1, right? They would be a 1 to 1 ratio if they were congruent to each other, because any side of this is equal to the other side of that. So 12,000 to 12,000 is a 1 to 1 ratio. 5.97 to 5.97 is 1 to 1 ratio, right? If they're congruent figures, of course, you're going to have a 1 to 1 ratio of similitude. We said for triangles more specifically, we have 6 ways to prove triangles similar. And of course, we use shortcuts like we do for congruency, but there's a difference. The abbreviations we use for congruency use what kind of letters, class?
Uppercase.
Capital letters or uppercase letters, while the similar polygons use abbreviations that include lowercase letters. What are the shortcuts for proving triangles similar? Give me as many as you can remember, Genesis. Angle, 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 that was the first one we talked about. Angle, angle, that was the next one. Leg applies only to right triangles, but if the two legs are proportional respectively, then the triangles are similar. SAS, where the two sides are proportional and the included angles equal. There was not, because that's the same as angle. Who needs the side when you got two angles? Missing two. Side. If all three sides are in the same, have the same equal ratios or proportional, then the triangles would be similar. And then the last one?
Side.
No. For a right triangle, just one acute angle would be sufficient to show that the triangles are similar. Now, of these, I said most of the time, we're going to end up using which one, Genesis? No. Why would I use 3 if I can get away with 2? I am lazy. I'm going to go with the 2. So this is the one we're going to use most of the time. Then from there we said that if triangles are similar, then I know that the corresponding angles would have to be equal. And if I know that triangles are similar, then I know the corresponding sides are proportional. We have 2 5-letter abbreviations. Quentin, give me one of them. CSSTP. Class, say it with me. What this stands for: corresponding sides of similar triangles are proportional. And this is a very important 5-letter acronym, because the best way to show that lines are proportional, line segments rather proportional, would be to get, class, similar triangles, and then use CSSTP, right? So anytime we're looking at a proof that says get these lines similar, get these lines proportional, this is going to be my go-to. Now there's 1 or 2 times we're going to realize you can't do it. And we're going to have to find another way. But other than maybe once or twice this entire year, proportional lines, that's my go-to almost every single time. Now the other 5-letter acronym I wanted you to know, we really don't use that often, Ethan. In class, let's say this together, what it stands for. Corresponding angles of similar triangles are equal. You'd really only use this maybe if you were using maybe one of these methods to get the triangles similar in the first place, where you knew a whole lot about the sides, didn't know a whole lot about the angles, then maybe, okay, yeah, that means the corresponding angles of the similar triangles are equal, but since most of the time we're using angle, we already know the angles are equal. That's not the issue. The issue is the sides. So very rarely used, but CSSTP we use quite a bit. In fact, let's go ahead and do a proof now that uses some CSSTP. Go and get out just some paper. This doesn't have to go in your notebook, though you're welcome to put it in the class notes section if you'd like. I want you to draw a parallelogram on your paper. I'm going to draw a parallelogram on your paper. And since I'm in a boring mood, we're going to name it ABCD. What I want you to do is to pick some random point on BC. Doesn't really matter. Not the midpoint. Make sure you're not going with the midpoint. We don't want to assume things that aren't necessarily true. So I'm going to go closer to B. You can go closer to C if you want. Really doesn't matter. And then join A to whatever point you happen to pick. The next thing we're going to do is we're going to take this A, or call this point P. We'll call it point P. We're going to take this AP line and we're going to extend it so it keeps going up, 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 up. At the same time, we're going to extend CD so it goes over, over, over. And eventually, these 2 lines, which must not be parallel. Why can these 2 lines not be parallel, Chris?
Because they'll never meet. Alright, okay, well.
I told you that these 2 lines will meet, which means they aren't parallel. How do you know? Fact check me. How do we know this line can't be parallel to CD? Anybody?
The AB's already
AB's already parallel. It's a parallelogram, right? So if AB's parallel through a point, only one straight line may be drawn parallel to a given line. If AB's parallel, this ain't it. So we know it's going to eventually intersect, correct? So let's go ahead and take this line. Let's go and extend it up. Let's go and extend this line over until eventually they meet. Call that point O. And call that point O. Here's what we're given. We're given parallelogram, ABCD, with P any point in BC. We're given triangle ABC, or excuse me, parallelogram ABCD with P any point in BC. You can tell we do a lot with triangles. AP and CD are extended to meet at O. AP and CD are extended to meet at O. Here's what we want to prove. I want to prove that the length of segment AP is to the length of segment OA. Pause. As BP is to DA.
Thank you, sir. I missed that voice.
Me too.
That's right.
I wish we wouldn't have skipped the stories, no?
Yeah.
There we go.
All right, let's try that again. AP is to OA. So this little piece is to its entire line, that ratio, as BP is to DA. As BP, this little piece, is to this whole other side here, DA. AP is to OA as BP is to DA. That's what we're trying to prove. Once you have this down 2 columns, statements, reasons. I'm going to get down your first statement and your first reason. All right. Playing Genesis. All right. Reason? All right, we got a parallelogram, therefore we have parallel lines. Alluded to it earlier. Got that there. All right. Any other clang? Chris?
Well, now that we have parallels, we have angles.
Yeah, we do. We've got a whole lot of angles, in fact. I'm going to go ahead and number the angles at A, 1 and 2. The angles at P, 3, 4, and 5. The angles at C, 6 and 7. And I think that takes care of all the angles. There's only 1 at D, 1 at B, and 1 at O. So we've got a whole bunch of angles numbered here. What kind of equal angles are you thinking that we can clang off of our parallel lines?
Well, when angle 1 equals angle 3.
Good. Angle 1 would have to equal angle 3 because they are...
what is that? Corresponding? No, opposite. Interior.
Helping class?
Alternate.
Alternate interior. There are alternate sides of the transversal. So, yeah, angle 1 equals angle 3 because... How would we say it, Chris?
Definition of parallelogram?
Well, definition of parallelogram tells me I have parallel lines. Then you said because lines are parallel, we know 1 and 3 are equal because they are...
I literally, you just said it. They're alternate. So, in parallelogram...
Not necessarily even in a parallelogram per se, but just with parallel lines. Ethan, helping?
Alternate interior angles and parallel lines are equal.
Yeah, alternate interior angles of parallel lines are equal. You could also say, well, if the lines are parallel, then the alternate interior angles have to be equal. I mean, you could write all that out as well. Just a little bit more concise. Here, but yeah, 1 and 3 are equal.
So it's 2 and 4.
Now, careful there.
No,
Look
they're
at
not.
2.
They're not.
Yeah, 2 is formed by this line and the transversal. 4 is formed by this line and the transversal. And these two lines are not parallel. So no, 2 and 4 would not be equal.
Would 3 equal 5?
3 would equal 5, though
That-
that's
that's
not
helpful.
because of parallel lines, but because of
vertical angles.
vertical angles. We could say that. Angle 3 equals angle 5 because
Vertical angles are equal. Always equal. And likewise, 1 plus 2 equals 6.
why is that?
Because in a parallelogram, opposite angles are equal.
Okay, you said A is equal to angle 6, and A equals 1 plus 2. So by substitution, 1 plus 2 equals 6. You take 3 steps to get there. I don't know that the sum of 1 and 2 equaling 6 is particularly helpful, but it's not a false
Would C,
statement.
would 7 equal D?
Okay, so you're saying that D here and 7 here would be equal. Let's give someone else a chance to talk here. Audrey, he's right, why would 7 and D have to be equal? Quentin, help her. Ethan, help them all.
Corresponding angles.
They're corresponding angles. Do you see it? Here's my parallel lines. Here's my transversal. They're both on the same side of the parallels. They're both below the transversals. They're in matching spots, aren't they? So corresponding angles of parallel lines are equal. We're just having a good old time with equal angles, and we're not even done. We got more we can talk about. Audrey, do you want to comment on any equal angles here? There's all kinds of equal angles we could play around with. I feel like Patrick Mahomes and they signed a wide receiver. It's just, yes.
You mean when they sign O line?
I'm sorry? Angle D and angle B. Why would D and B be equal? All right, so what would we say for our reason? You're right, they're equal, but how do we state the reason? It's like, I don't know why, I just know it is. Someone help?
Alternate interior.
They're not opposite interior. They have nothing to do with parallel lines.
Alternate interior.
Oh, angles of parallel lines.
Opposite angles in a parallelogram are equal. By the way, opposite sides of a parallelogram are also equal. We never even said that,
I
right?
was going to say that next.
Now, okay, let's tell you what, let's do that. Let's say that D equals B, A equals C, AB equals CD, and DA equals CB, because opposite sides and opposite angles of a parallelogram are equal. That was our theorem 19, our very first parallelogram theorem. So we got a whole bunch of equal lines. All right, we've got a whole bunch of equal angles. I mean, I guess technically we might even be able to get still more angles if we wanted to. Anyone see another set of angles we haven't even talked about yet?
Would 4 equal D?
4, no, because 4 and D are not opposite angles in a parallelogram.
So
Furthermore, since we said B and D were equal, Chris, I know 4 can't equal B. Someone tell me, why can 4 definitely not equal B?
because then 3 plus 4. Wait, no.
Because AP is not parallel.
Well, yes, but there's an even more pronounced reason than that. That's kind of an indirect thought is, well, if they were parallel, then it would be. So since they're not parallel, they can't be. But there's an even better thought. This is an exterior angle to this little triangle down here, isn't it?
Mm-hmm.
Exterior angle can't equal an opposite interior angle. It's greater than opposite interior. So 4 is bigger than B, therefore 4 is also bigger than D.
Would 6 equal 5? So then therefore 6
No, because
not?
6 is also exterior to this triangle. Right? Here's a triangle. This is an opposite interior angle like O. So no, 6 is bigger than 5. It's equal to 5 and O put together, I suppose. But anyway, there's another pair of angles. Jamie, you look like you're thinking of something.
Is 1 equal to 5?
Yes, 1 and 5 would be equal because 1 equals 3, 3 equals 5, or because they are corresponding angles. So we could say 1 and 5 equal, here with the whole 7 and D equal. Not being particularly efficient on this proof, but we're having a great time getting equal angles everywhere, and we're not done.
Okay.
We don't even have to state this next one, but if you wanted to lump it in there, 2 and O What kind of angles are 2 and O?
That would be
Not our basketball team. Anyway,
opposite. Opposite.
2 and O. Sorry, angle 2 and angle O.
Opposite interior.
Alternate interior. So we
Yeah.
could put that in number 3 if we wanted to. Angle 2 equals angle O. Now, it's not a 0, that's an O. All right. But yeah, I mean, there's all kinds of angles. Now, we kind of got distracted. We were just having a great time. Let's get back to what we're trying to prove. I'm trying to prove line segments are proportional. And anytime I want lines proportional, class, I got 2 thoughts. First, let me get some similar triangles so I can use CSSTP. The question is, which triangles have to be similar? So going back to yesterday's lesson, how do I know which 2 triangles I need, Chris?
The proportion. Just look at the proportion.
Look at the proportion, and the proportion tells me, because I'm going to look first at
the different characters.
Yeah, specifically
On the antecedent.
the antecedents. I'm going to start with the antecedents, and there should be 3 distinct letters there, and there are. What are the 3 distinct letters? A, P, and B. So I know triangle A, P, B, that's this little guy down here is one of my 2 triangles. It needs to somehow be similar to which other triangle, Quentin?
OAD.
OAD. Look at all the consequence. Oh my.
A big triangle.
So this great big one needs to somehow be similar to this little bitty guy down here. Again, not same size, but same shape is what we're trying to prove.
Why wouldn't an OPC work? Would OPC work? Is that all?
Do we see O, P, and C in the bottom? No, I see O, A, and
we
D.
could.
So I want those triangles so I can get those lines.
Well, we have angles equal.
Now, in order to get them similar, I need to probably use angle, right? So do I have any angles in these 2 triangles that are already equal?
Yes.
Yeah, B and D, for instance, there's one set of angles. And 3 and 1 were already equal, right? Up here, so there's another set of angles. And for that matter, 2 and O were also equal. We didn't really need it though, so technically we don't just have angle, we have angle. Why not? So now, if we hadn't taken time to say 2 and O, we were still good. We still would have had angle, but I didn't need any of these other things. I just needed that much. And so number 7, we do know, yes, triangle APB is similar. Hold on. A is the angle at 2, right? That corresponds to O. All right. P is the angle 3. That corresponds to 1. That's the angle A in the other one. And B corresponds to D. So the letter order did work out. But APB is similar to OAD by AAA. Or if you were to write AA, it wouldn't be wrong. And so, since the triangles are similar, class, the corresponding sides have to be proportional.
Yeah.
If triangles are similar, corresponding sides are proportional. So we can state, Ethan, who needs some redemption, that
AP is to OA as AP is to DA.
reason class, which stands for corresponding sides of similar triangles are proportional. Questions on this? Turn to page 209 in your textbooks. Page 209 in your textbooks. Let's do one more proof involving these proportion thingies. Oh, that's a good math word. All right, page 209. And look at number 9. There's no picture given to us, but Kendall, there at the top of page 209, in fact, the very first thing on the page, number 9, go ahead and read it for us.
Is any point on board AB and BC is perpendicular to diameter AB. Prove AC times BD is to AB times BC.
All right, go ahead and read it for us again, if you would, Genesis, nice and loud.
If P is any point on board AB and PC. I'm supposed to read number 9.
Number 9, read
Okay.
it.
If P is any point on chord AB and PC is perpendicular to diameter AD, prove that AC times AD equals AB times AP.
All right, what do I need to draw first, class?
Circle.
A circle. And like it doesn't mention circle, nobody uses what two key words? Chord and diameter. We obviously need a circle. Now, once we've drawn the circle, we need to draw what two lines? AB and AD. We've got a chord AB and we've got a diameter AD, and notice they both use the letter A, which means they both start from the same point. So pick a point on your circle, or badly deformed egg as I've drawn it. We're going to have some chord, which we'll call AB, and then you're going to have to guesstimate the center. I'm going to go ahead and call it O, and you're going to need to draw a diameter AD. You see what we've got going here? We've got a chord, we've got a diameter. Now, in my chord AB, I've got to pick any point and call it P. Right? Pick any point and call it P. So I'm going to go closer to A. I'm going to just pick a little point down here. I'm going to call this point P. But from P, I've got to draw a perpendicular down to the diameter AD. It says that PC is perpendicular to AD. So draw a little perpendicular to your diameter. So you've got chord AB, where P is any point in the chord, and then PC is perpendicular to diameter AD. That's our picture. Does that make sense? All right, given. Well, what did I draw first? Circle O. With diameter AD and chord AB. I could say P is any point in AB. I'm lazy, but I do need to specify that PC class is perpendicular to AD. And then we want to prove, what again, Kendall?
AC times AD times AP.
AC times AD equals who?
AB times AP.
Times AP. Did I write this correctly, Kendall? Okay, just making sure I was hearing you correctly. All right, now wait a second. That's not a, well, careful. A isn't a value unto itself, it represents an endpoint. That's not a proportion. What's that doing in here? We're supposed to be talking about proportional lines. I must not have paid very good attention last night when I was planning this.
It would be like it's the means and the extremes.
Ah, if the product of two quantities equals the product of two other quantities, either pair of values may be used as the means and the other as the extremes in any proportion, right? So this time, I'm not even being asked to prove a proportion, but from what I'm trying to prove, I could make a proportion that once proven true by similar triangles in CSSTP would give me this statement. So without knowing anything about this figure, no matter how you drew your circle, no matter how big, no matter how you drew your chord, no matter where you picked your point, anytime you pick any point in any chord, draw a perpendicular down to a diameter from the same point. The product of the piece of the diameter and the whole diameter will always equal the product of the whole chord and the piece of the chord. That's what we're proving, without having any numeric lengths to go off of. Go ahead and set up two columns, statements, reasons. Go and get down your first statement and your first reason. Go largely analytic on this one. Though there is technically a clang, we should probably take care of the clang real quick.
There's two.
Two clangs. Ah, what's the second clang you see?
Well, first I see diameter.
What does diameter tell me, Chris?
2 equal sides, or
two equal.
Chords.
We call them, class, semicircles. That's a subtle clang right there, but it is a clang that we actually will want to use let's go ahead and specify that, now notice all the action is above the diameter, right? So although technically there are two equal semicircles, I really only care about the top one. I'm going to specify that arc ABD is a semicircle because a diameter divides a circle into two equal semicircles. A diameter divides a circle into two equal semicircles. That's a subtle claim, but it is one we were going to come around to through the analytic method anyway, so I don't mind getting that down early. Great call there, Chris. What's the more obvious claim, though? Quentin? Perpendicular. In Genesis, what's the claim response to perpendicular?
Equal segments.
Not necessarily. Claim response. Right angles, right? So I'm going to go ahead and number this angle 1 and this angle 2. They're kind of small in there. I'm not even sure if it's coming up on the video well, but 1 and 2 are my two little angles at C. And so we could state Genesis that. And the reason. All right, so that kind of takes care of the claim. I want to think analytically, though. And we've already started the analytic process because we said, I don't know how to prove two things multiplied equal two things multiplied, except that if I have a product of two things and it equals the product of two other things class, I can make a proportion. So let's think what proportion would be most beneficial, because remember, there are literally 8 different ways you could write the proportion. Let's see here. Quentin, I just called on you. Jamie, you were the one who thought of the means and the extremes thing. You should have it copied on your paper already.
No, I do. I just wanted to see it. I couldn't really see it.
You shouldn't need to because you have it on your paper already. But anyway, Jamie, what's a proportion we could set up here?
AC is to AB as AP is to AD.
All right, so she put AC in an extreme spot, AB in a mean spot, AP in the other means spot, and AD in the other extreme spot. Now here's the deal. Because there are 8 different ways to do this, I want to do this in a way that works well for me. If we go with this arrangement, the next logical thought is, what two triangles are we going to need, right? Thinking analytically. If I can prove this if this proportion is valid, correct? But what triangles would be needed, Jamie, to make that proportion work?
ACP and ABD.
All right, so let's see. ACP. Do I see a triangle ACP, class? I do. Do I see a triangle ABD?
No, you have to make
No, but it would be fairly easy to make, wouldn't it? So I think this is a great way to set it up. Now, if she had done it, let's see here. Let's suppose Jamie had said this. Well, now I'd have ACB, I'd have to draw that line, and APD, I'd have to draw that line. That would be a little bit more of a challenge, wouldn't it? But the way in which Jamie set it up works really well for me. Let's go ahead then and draw BD. Reason, class. So our strategy is clearly laid out for us here, Audrey. I want two similar triangles. I want ACP, I want ABD, I want them similar. How do you think we should try to go about getting these two triangles similar? Yeah, which angles, just kind of looking at it here, do you think maybe we should try to get equal? Angle 2?
Angle 1 and 2.
All right, now, we could say 1 and 2 are equal. Here's the problem, Audrey. 1 is in triangle APC, but 2 isn't in triangle ABD, is it? So 1 and 2 being equal doesn't really help a whole lot, does it? Maybe another angle. Let's stay with Audrey here. And of course, we already got that dotted line. So we're looking at the big dotted triangle and this little bitty guy here.
Can you do inscribed angle equals half time?
What inscribed angle are you thinking, Audrey?
ABD would equal half AD.
ABD. So you're talking about this angle here And that's an angle inscribed in a semicircle. So I already know this has to be A. So that's how the perpendicular is going to help me. Does that make sense? That gives me right angles, but because I have a semicircle, ABD must also be a right angle. Number 5, Audrey, let's go ahead and state that. Because have an any angle. Yeah, absolutely. Yeah, any angle inscribed in a semicircle is a right angle. And now, Audrey, it's not 1 and 2 that we want to get equal as right angles, but rather 1 and angle B, or angle ABD as you called it, but it's not wrong to just call it angle B. Angle 1 does equal angle B because all right angles are equal. So there's a pair of equal angles. All right, 1 down, 1 to go. Kendall, we're going to represent the 10th grade here. Get the other angle. What angles are left in the big triangle, Kendall? And angle A and D are the 2 angles left, right? What are the 2 angles left in the little bitty guy? A and P, okay? So here's the question. One of those angles, A and P, has to equal one of the other angles, A and D, right?
Angle A equals itself.
Ah, yeah, angle A is shared. Angle A is in both triangles, so we could say number 7, Kendall, that
Angle A equals angle A.
by,
Identity.
and there's my other set of angles, so therefore, hey, if I've got angle class, I've got, which means I've got similar triangles. Yeah, number 8, Genesis, we should write that.
Triangle ACP is similar to triangle.
Now pause before we write the letters. What needs to correspond to the angle at A? A, okay. What needs to correspond to the little angle at C? We call it angle 1. What angle corresponds to the angle here at 1 or C? Referring back to the proof, B. We already said that 1 and B were equal, so C needs to line up with B. Okay, and it does. So again, the reason I point this out is don't assume the letters will always happen to be in the right order. Check and make sure. But yeah, the 2 A's do line up. The C and B do line up, which means the P and D have to. And the reason we know they're similar, Genesis? What's the number 1 way of getting similar triangles? Chris, help her. No, number 1 way of getting similar triangles. Angle. That's what I got right there. That's why they're similar, is because I have 2 equal angles. Triangles have to be similar. And now that I know the triangles are similar, Chris, then number 9, I know that
AC, AC times AD.
Huh? Help, Jamie.
Is it AC is to AB as AP is to AD?
There we go. I know that AC is to AB as AP is to AD. The reason I wanted similar triangles, class, is so that I could get some sides proportional. So I could get the proportional sides by, class, CSSTP. I got my similar triangles, therefore sides are proportional because corresponding sides of similar triangles are proportional. Now, this isn't what I wanted to prove ultimately. I wanted to prove this. How do I go from here to here? Don't overthink this. What? No, multiply the means and multiply the extreme. In other words, the product of the means equals the product of the extreme. So number 10, since this proportion must be true, because these are corresponding sides in similar triangles, then the product of the means and the product of the extremes must be equal. So yes, AC times AD, the product of the extremes, does equal AB times AP, the product of the means, and that's our reason. Product of means equals product of extremes. There we go. questions on how these proofs work with similar triangles, proportional sides, or in some cases, you're not even technically proving proportional sides. Well, you do as a way of getting there. Questions on this? All right, theorems, corollaries, section of your notebook. Theorem 60. Theorems, corollaries, section of your notebook. Theorem 60. Now, you'll recall corollary 53-2 had a whole bunch of parallels and 2 transversals. Y'all remember that? You already had that on a quiz, you better remember that. Theorem 60 is kind of the opposite. It's not a converse statement, but it's an opposite idea. In that Theorem 60 deals with multiple transversals and just 2 parallels. Theorem 60 says this: if two parallel lines are cut by 3 or more transversals, I do 3 plus, meaning 3 or more. If 2 parallel lines are cut by 3 or more transversals, passing through a common point, so not just random transversals, but specifically transversals that all come from the same point, so concurrent lines, right? If 2 parallel lines are cut by 3 or more transversals passing through a common point, comma, then the corresponding segments of the parallels are proportional. If 2 parallel lines are cut by 3 or more transversals passing through a common point, then the corresponding segments of the parallels are proportional. So here's the idea. I have just 2 parallels this time, but from one common point, I've got a whole bunch of transversals. And we'll call the parallels M and N, line M, line N. They are parallel as they appear. Let's call this point P. We can call this point A, this point B, this point C, this point D. We'll call this W, X, Y, Z, and so forth. We want to prove that the corresponding segments of the parallels are proportional, so that this piece is to its matching piece, as this piece is to this piece, as this piece is to this piece, and so on and so forth, right? Kind of like what we did when you had lots of parallels and just 2 transversals. Now you've got 2 parallels, lots of transversals. Where's the idea? If the lines are parallel, you know those 2 angles are equal, right? And these 2 angles are equal because corresponding angles of parallel lines are equal. Which means that this triangle, PAB, has to be similar to this triangle, PXW, right? They gotta be similar to each other because they have angle-angle. For that matter, this little angle at P equals itself by identity. They have angle-angle if we really wanted them to. If that's true, then this side, AB, is to this side, WX, as any other 2 corresponding sides. Let's just say PB is to PX, correct? CSSTP. On a similar note, we could say that this angle equals this angle, and this angle equals this angle. So we could say that these 2 triangles, this little top guy and this whole guy here, they're proportional. So that we could say that BC is to XY as any other 2 sides. Let's just say PB is to PX, for instance. You realize you could keep going with this pattern, right? These 2 triangles would have to be similar, and you could just keep going and going and going. Well, what we do is we create common ratios. Well, AB is to WX as PB is to PX. BC is to XY as PB is to PX. So these 2 ratios equal the same ratio, therefore these are equal to each other. So that's how we would show that AB is to WX as BC is to XY. And we can keep going as CD is to YZ, as DE, for instance, is to ZQ, as, you get the idea? This is this, is this is this, is this is this, is this is this, is this, it just keeps going and going and going. Questions on Theorem 60. Look in your books at page 209. Many of you are still there. Page 209. If you're not, go ahead and turn there. And let's look at just a couple of quick questions, kind of build off of this thought. We're not going to take time to do these proofs, but I want to kind of talk through them here. Page 209, number 1. Go ahead and read that for us if you would, Genesis.
From the trisection points of side AB of triangle ABC, lines are drawn to C. Prove that these lines trisect all lines parallel to AB and are terminated by the other two sides.
All right, so here's the idea. We've got trisection points of AB. We'll call them XY. So I've got 3 equal segments. It says lines are drawn to the vertex from the trisection points. Prove that if you draw any other line parallel to AB in between these sides, that they'll all be trisected. Well, we just proven now we would have a series of parallels, right? So this would have to be to this, as this is to this, as this is to this. But if these are all equal, then these would have to be equal, because they would have to make equal ratios. And of course, you can do that with this line, the same thing. This is to this, as this is this, as this is this, but they're all equal, so they're all equal. And you just keep on going, right? So any line drawn, once you've got trisection points and lines back to the vertex, any line you draw parallel to the base is going to be trisected by those lines. Look at number 2. Read that one for us, Chris.
AB is a chord of circle O, and radius OC is perpendicular to AB. The tangent at C is drawn in the radii The tangent at C is drawn and the radii to A and B extended to meet the tangent at D, and you respectively prove that DC equals EC.
I feel like we may have actually done this proof another way before, but this theorem certainly makes the concept easier to prove. We've got a circle O, we've got some random chord AB, and we've got a perpendicular radius OC. Now remember, if a radius is perpendicular to a chord, class, it will bisect the chord. And the arcs, by the way. So we said, well, what if we draw a tangent at C? Well, tangent means what? It means it's going to be perpendicular. 2 lines perpendicular to the same line OC have to be parallel to each other. So we've got 2 parallels. Well, what if you then drew OB and extended it, and OA and extended it? Well, now we have 3 transversals passing from a common point intersecting 2 parallel lines. So this segment is to this one, as this one is to that one, but since these are equal, those are equal. So yeah, DC and EC have to be equal. Any questions on that? Questions at all on Theorem 60? For homework this evening, you're going to do page 208, number 6. Page 208, number 6. Now let me help you get the picture. So if you have your book open at page 208, that's going to help you. If you have your book open to page 208, that's going to help. Your homework is page 208, number 6, but I want to help you get the picture here very quickly. Go ahead and read page 208, number 6 for us, Ethan, nice and loud.
Diameter RS is extended to D, and the perpendicular at D makes chord and is extended at F.
All right, that's a whole lot of stuff in there, right? But we know the first thing we got to draw, class, is
Circle.
a circle. And in the circle, we should draw a diameter, and we should call it RS. So on your paper that you're going to use for homework, go ahead and draw the circle with the diameter RS. It then says the diameter is extended to some point called D. So we're going to extend this line out, Brecken, you may go, to some point, call it D. However far you want to extend it. Probably not too far because that's more work. And then at D, we have to make a perpendicular at D. And it says that this perpendicular at D meets up with a chord called NS. So watch. There is some chord that goes to S from some point N that when extended meets up with the perpendicular. So the easy way to do it is actually to draw it backwards. Draw from the perpendicular through S here. So here's the chord NS that's extended to meet the perpendicular at M. That's our picture. Diameter, chord. The chord is extended, the diameter is extended. And from the end of the extension, we can draw a perpendicular to the end of this extension. That's what we're dealing with tonight in homework. Page 208, number 6, there's your picture. Don't forget, notebooks due Tuesday and exam Tuesday. You've got your notebook check sheets today. Make sure you check things, especially over the weekend, to make sure you're ready to go. You are dismissed.